Yes, sir.
Right. So let's imagine this example. This will definitely help you to understand friction if you cannot understand up to this point. Uh, let's say we have a horizontal counter and we are sending a book sliding across a long horizontal counter. So what happened? As expected, the book slows and then it is going to stop. This means the book must have an acceleration parallel to the counter surface in the direction opposite to the book's velocity from the Newton's second law. Then a force must act on the book parallel to the counter surface in the direction opposite its velocity. That force is frictional force. So I can basically draw that one like this. Here we have the counter. This is the book. This is the direction we are sliding the book. And through this surface, we have the friction. Okay. Right. So let's, as I said earlier, the friction is also a self-adjusting force. Okay. Now, to understand that, we can take three scenarios in this with the same book actually, right? Three different scenarios. So let's consider this yellow object as the book. Okay, here we have the counter, and the first scenario is there is no attempting at sliding, which means the book. What is the velocity of the book then? Velocity of the book is 0, which means what? The book is at the rest condition, right? So if the object is at its rest, is there any friction force there? What is the value of the friction force? It is going to be 0. Now you can see here, uh, what are these two forces in the first diagram? From the gravity point, this is the weight and this is the reaction force, right? Or you can say normal force, perpendicular force. This is the action and the reaction force, the weight and the reaction force. Then the second scenario, now we are now we are applying a force to the book. And when we apply a force, what happened to the book? It gains some velocity over the time, which become an acceleration. Now the object is actually moving, right? This one is moving in this direction, the second diagram I'm talking about. And due to this force, what happened? There is an friction force applied in the opposite direction through the surfaces. Sorry, in this case, actually, I forgot to mention, please forget what I said for this second case, actually. Let's say this book, for this book, actually, let's say we are applying a force to this book to move. Let's say it is around 5 newtons, okay? 5, let's say 2 newtons. Applied force is now 2 newtons. However, even though we apply 2 newtons, let's say the book is not moving at all. The book is not moving. What is that case? The book also, what happened is that book is not moving because the friction force is also happened to be exist. However, as a self-adjusting force, the friction is also going to be 2 newtons. Then what happened? These two are balancing. Even though there is a friction force, the object has no motion, right? Object has no motion. Now, if you cannot understand this one, let's take example like this. Okay, let's say your car is stopped. Okay, your car is stopped, or let's say there's a large dining table. There's a large dining table, and if you apply a force to that dining table, let's say from with using only one hand, let's say you are applying only 2 newtons. Now, in some cases, it is not going to move, right? The table is not going to move. What is the reason? Even though you apply 2 newtons to that large table, the friction is also increased up to 2 newtons with the 4 legs of that table in the opposite direction, and there is no motion. Okay, this is the second case. The object is still there. So in these two cases, object is still not in the motion. The third case, in the third case, instead of 2 newtons, let's say we are applying 5 newtons. Now friction also become 5 newtons. Still it is not moving. Still it is not moving. It also can be happen, right? It also can be happen. Now for a large table like that, you should at least have 100 newtons or more than that. Just assumption, just assumption. Now we look at the next case, the figure D actually, right? Force is now even stronger, but it is balanced by the friction force. Still, it doesn't have no motion at all, right? Still, the force has no motion at all. We call this one as a static friction force actually, right? We call this one as a static friction force. Let me show you the diagram actually, then you can understand. Okay. Now, after certain time, this this object has to be moved, right? This object has to be somewhat moved. However, let's say you have a maximum value of maximum static friction force. Let's say for this one, it is, I just assume a value, it is 50 newtons, right? Which means up to 50 Newton, even though you applied the top 50 Newton here, does the object going to move? I'm applying 50 Newton to the object, but maximum friction force or the maximum static. Why we call this a static term? What is the meaning of that static? Static means not moving, which means it is stationary. It is not moving at all, right? So these two forces are balancing with each other. Still, there's no motion. However, this is the limit. This is the limit. Now, if this force become 51 Newton, if I apply 51 Newton, what happen? 50.5 Newton, the object should move, right? Object should move because there's a resultant force now. That is exactly the next case, right? Okay. Finally, the applied force in the second, in the middle diagram, finally the applied force has overwhelmed the static friction force. Let's say 50 Newton. Then what happened? This block or this book is going to slide and accelerate. However, it is kind of a weak kinetic friction force. Now the static term, static frictional force become kinematic or kinetic friction force. Kinetic means if any object is in the motion, we call that one is it is in kinetic condition. If it is not moving, no motion, it is static. That is why it is called as static friction and kinematic friction or kinetic friction. Now it is the same case. Okay, let's look at this one. Okay, right. So basically the force is applied in this direction and the friction is in this direction. However, the applied force is increased or larger than the static friction force. So it is going to accelerate in this direction. Okay. Now we have the kinematic friction force. And if you, however, increase, right? If you, however, increase this applied force, what happened? What do you think about the friction? Now I am applying, let's say, 200 newtons. 200 newtons I am applying as a force. What do you think about the value of the friction force? Now, as I assumed earlier, I assume that maximum is 50. Now, is it going to be friction going to be 200 newtons? If this friction become 200, there's again there should be no motion. So after the maximum static friction force, let's say 50 newtons, it is going to keep constant. Whatever, if it is 2000, 3000, still according to the object, the friction, static friction is going to be 50 newtons. So it is going to remain constant when it is started to move. Now we have talked about 6 figures. Now I can put them all into one diagram. You can easily understand, right? And in this case, you identified that there are 2 types of frictions. One is called as static friction and the other one is called as a dynamic or kinetic friction. Kinematic means in the motion, there's no motion in the static friction. Now, starting from the, let's look at this figure. You have to remember this figure actually. It is very easy to understand, right? Here you can see the static frictional force can only match growing applied force. Okay. Now there are two let's say green color. So for this side, I'll get the frictional forces, okay? Frictional forces. And to this side, either you can take the time or the applied force, right? Either you can take the time or applied force. Okay. Now let's put some values and compare what happened in here, right?
Excuse me, sir. Isn't there limiting frictional force in it?
Sorry.
Isn't there limiting frictional force in it?
Yes, here you can see the limited friction force, this point, the peak of
Uh,
this one. Okay. So now you can see if there's no motion, right? If there's no applied force, which means the 0 point, there's no friction force at all, right? No applied force, no friction force. Then if you apply 5 newtons, friction force become 5 newtons. That is how this chart has been drawn, right? If it is 10, friction force become 10, 15, 15, 20, 20, and let's say the maximum, that maximum static friction force point, the peak actually, this one, let's say 50 newtons. 50 newtons, the matching magnitude friction force is also going to be 50 newtons. Now up to this point, you have to remember, up to this point, this is the static side. Okay, this is the static side. And after you break that barrier of the maximum value, maximum static friction force, this point, what happened? Whatever the applied force it reduces actually up to certain point and it become a constant value. Now the friction value is constant, whatever the applied force we are applying, it is in this constant condition, right? And okay, now in this in the left hand side, this is the kinematic side of this chart. Let's move back to a more clear chart. Okay, that maximum, as I said earlier, the maximum static friction force is also called as the limiting frictional force. Okay, it is the same term. Uh, for example, you can see a man tries to push a heavy box on a rough horizontal surface. Like if the weight of the object is very high, man cannot move this one, So which means there's a certain, in order to move this heavy box, you should apply actually more than the limiting friction force, right? Now this is a good diagram, but it is not much of a clear one. Okay. So this is a more simple chart. You can easy to remember. This is the applied force. This is the friction. Now you can see there's a constant growth, a proportional growth actually in this side, in the static side. And once you pass the limiting static friction force, the friction force somewhat lowered up to certain point and it keeps constant. So it become a dynamic case. Now to introduce these two static and dynamic condition, um, we can either note it down like Fs, which means the static friction. And for the dynamic or the kinematic one, we say Fk. Okay. Right. As I said earlier, friction, why we have to thoroughly go through the friction, because we can actually make a equation out of these frictions to find out the frictions. Now, in that chart, actually, in this chart, you can see only in the static side, the applied force is actually proportional to the frictional force. Applied force proportional to the friction force only in the static side, okay, up to only this point. After that, it is not proportional. Now, considering the proportional side, I can write down applied force is proportional to um, the reaction or the friction, right? Then I can write to take out this proportional sign. I have to multiply this equation by a constant. Now, this constant is called as the mu term. You can draw it like this, mu term. It's kind of a simple u. You don't have to italic this one. You can just write it down like this. So this is the constant, okay? And this is called as a coefficient of friction. Coefficient of friction. And since there are two conditions, since there is a static condition as well as kinetic conditions, you can say the coefficient of static friction, which is mu s. And if the object is in motion, you can apply the term mu k. If it is in the no motion, it is mu s. And you have to remember that there's another difference, which is actually, if I ask which one has the highest value, I mean, this is actually the mu s, and up to this point, we can use the mu k term for any question. So which one has the highest value? It is actually the coefficient of static friction has higher value than coefficient of dynamic friction or kinetic friction. Just you have to remember this one because in one earlier question for the MCQ, this one has been asked. So very simple thing. So mu is like mu s values are like 0.12 like that. Mu k is much smaller than that. Okay, or dynamic friction, kinetic friction, it's the same thing, right? So it is the same thing. So equation become F is equal to mu r. Like as per a typical example, you can just remember F is equal to mu r. Okay, this is the equation for the friction. F means the friction. Okay, F means the friction value. Don't remember this one as a force because I have seen that a lot of guys think that the applied force is the F. F is not going to be the applied force. This is going to be the friction force. And either in the question they might give the Fs, I mean mu k or mu s or mu k value. If the object uh, in the static condition, you have to apply mu s value multiplied by r. So what is the r? The reaction force. You already learned about the reaction force, right? Reaction force is what? So this is the reaction force. I'll get the red color. And here you can see this is what is this force. This is the weight. And from the contact force to top side, this is the reaction force. This is the R value. This force is R. This is the mg. And let's say this is 20 Newton. Let's say that force is P. What is the friction then? Friction is F. This is the friction. So if I say that this is in this question, I will give you the mu s value as 0.3. So what is going to be the friction force value then? If the mu s is 0.3, what is the R value? R value is actually going to equal to the mg, right? Why? Because in the vertical direction, this object is stable or it is vertically in equilibrium, but horizontally it is moving. So however, the R is equal to mg. So which means, let's say I would say the weight of this object is, the mass of this object is 3 kilograms. Then what is the R value? It is going to be 30. How it become 30? Because gravitational acceleration is 10, it is become 30. So mg is 30, 30 is equal to R, mu s is 0.3. Then the friction applied between this contact forces, I think 3 by 3, 9, 9 newtons, right? 9 newtons. 9 newtons. So if I apply the force of 20 newtons, the friction adjacent to that is 9 newtons. However, that is only for uh, in static condition. But if it is in motion, you have to apply that mu k value. That those things will be given in the exam. Those values. Okay, you can see the mu k and mu s. Okay, right. You can try to do this example actually. Or we can try this one now. Right, a man trying to push a package of case weight 300 Newton. You can give me answer actually in the chat box, the final answer. Before that, you can always in every question draw a free body diagram, right? It's always easy. Don't use the imaginary things. Just put every detail into the diagram. Okay, so weight is 300. What is the minimum horizontal force required to slide it? Okay, that's a good question, which means in order to push this one, what is the minimum force? Let's say that force is, let's say it is P, okay? Let's say consider it one as P. This is 300. Yeah, and if the coefficient of limiting friction between the case and the flow is 0.3. Now this is the limiting friction force, coefficient of limiting friction. Now my question is it static or dynamic one? Limiting means what? It is the maximum static friction force, which means it is still a static friction coefficient. Then I can write down the equation F is equal to mu r. Sorry, okay, I cannot recall. Okay. Then this is going to be my R value, which is also going to be 300. And friction force applied in this direction. So it is 0.3 multiplied by 300, it is 90 newtons. So that is the minimum force required to slide this one, right? But it is still sliding? No, right? Is it still sliding? Now, F is not the applied force, okay? This is what? This is the friction. Friction is now 90 Newton. Now, is it the minimum value? Yes, it is the minimum force required. If this is 90 Newtons, if I apply 90 Newtons, is the object is going to move? No, right? It is not going to move. However, that is the maximum or minimum value required. Now, if I apply 90.1, then the object is going in the motion. The second one, finally, the man was able to push the packaging case over the floor. When he started pushing, he felt that the package case is easily moving with less effort. He only needed 87 Newton force to maintain a constant velocity. Okay, then calculate the coefficient of dynamic friction, which means the kinematic friction coefficient. Now, he's saying that after 87 Newton, he can easily move this one. What happened? What is the case? Now, the answer lies with that diagram, right? Answer lies with that diagram. You can see we already find out that this maximum limiting point is 90, right? This value is 90. However, you can see when the object is in the motion, that friction coefficient is somewhat reduced. That's what happened. So 90 Newton is the maximum limiting, but when it is in the motion, 90 Newton, less than 90 Newtons is required. Now it become 87. Okay. I believe you can understand that is the reason behind that, right? The reason I can say because mu s is larger than mu k. Then how to find out that value? So they're asking the dynamic one, Then this value is going to be, I can assume it as 87 Newtons, right? You can still use the F is equal to mu r, but since they're asking about the dynamic one, we can say mu k, okay? We have to take it as mu k. You can say F is equal to mu K or mu dynamic. You can say mu K R. They're asking to find out the mu K value coefficient. So this is the friction. Okay, sorry, my mistake. Here, this is not 87. The friction is actually 87, not the applied force. Applied force is what is the value? Is still 90. This is 87. That is why it is moving, right? So friction is 87, R is 300, mu K value is 0.29. Okay, I think that is obvious for you. Okay, shall we move into the next slide? And as an homework, you can try to find out what are the disadvantages of friction. You can categorize that and how to reduce that disadvantages actually, right? To reduce the heat between the mechanical components, what we are doing, we are applying that oil, right? That is why we have to oil our vehicles. And the advantages of friction as well. Okay. Right. Let's make our next part of the lesson. Since we already learned about the forces, right, different types. Uh, since the force, since the force is a vector, we can resolve the forces. If there are more than one or two forces, right, or any force diagram or force system, it doesn't matter whether for a single object, let's say they are applying like there are 20 different type of forces applied. However, sometimes you have to find out the resultant force when it comes to a single equation. Let's say F is equal to ma. However, for that object, let me draw the example. Now, up to this point, we have done very simple diagrams, right? It is like only one forces, only one force. Let's say we only do like one force, like this. This is the applied value, and what is the next one? So it is very easy to apply this equation into F is equal to ma equation, right? F is equal to ma. Uh, whether this one is 20 newtons, we can directly apply it as the F value. Now we need these resolving forces where we have to deal with the force system. Force system means, let's say another force applied in this direction, another one in this direction, another one is pushing in this direction, another one is applied in this direction. For the same object, you can see now how many forces applying. 5 separate forces are applied. So we basically call this one as a force system. Force system. Right? Now, in order to apply the force for this F equal ma equation, now we have a challenge. So in that case, what we have to do is that we have to resolve these 5 forces into one resultant force. One resultant force. And remember, these forces are actually coming with an angle, right? If it is not vertical or horizontal. Now this is a vertical one, right? This force is also horizontal. This is also horizontal. This is a vertical one. But there's a problem with the other two. The problem is actually you have to you have in the question you have to give us this angle actually this angle. Okay, whatever the angle from the horizontal or vertical. Let's say this is 30 degrees. From the 30 degrees, we have applied the force like this. From 60 degrees, another force is applied, right? So this is the scenario. I'll quickly go into that. Now you can see another force system here. Blowing in the wind, this spider is hanging in equilibrium condition. Now this is the spider. So this is his thread actually. There's a tension in this thread. And this is the force applied on him by the push of the wind. And the other one is the weight. However, there are force system. We want to find out, we have to resolve the forces. It's very easy. In the last week, actually, the last recording as well, I have discussed about this one. So this is how you can manage to resolve a force. It should not be in the x or y direction, but in an angular direction like this. Okay, it should be in an angular direction. Let's try to resolve this F force into, first of all, into two component, the vertical and horizontal component. The vertical component, let's say if in this question 30 degrees is given like this and this is 20 newtons. Now they are asking what is the vertical component of this force, what is the horizontal component. If the angle is given, if the within the, I mean, for the angle side, if the angle is in one side, whatever that side is, you have to consider this one as a cost times the angle, which means that the equation is force 20 multiplied by, if it is in the angled direction, this become cos angle value, cos 30. In the opposite direction, it is the force sine theta, which means 20 sine 30. However, let's take another example. Let's take the same example. Let's say the angle is given in here, 60 degrees in here. Then how to write down the two components? This one become again a cos value, 20 cos 60. And the horizontal component, this become 20 sine 60. Sine 60. Now, can you understand the difference? You have to remember the main thing in this resolving forces is that you have to take any angular force out there, take it into two vertical and horizontal component, because in that case we can easily resolve the forces, right? If it is in the same side we can add, if it is in the opposite side we can deduct. Okay, you have to give me a second here. Right. So whatever the side angle lies, you have to apply it as a cos. That is the thing you have to remember here. Right. Then you can, once you resolve this one, you can forget about this force, because we can use these two vertical or horizontal forces to do any correction. Right, I shall stop the share.